The resistor, so simple, yet so complex. So many mysteries, so many unknowns. There has to be a way to crack the code. How much resistance does this resistor resist? I traveled far and wide, looking for the man, the only man, that can help me on this journey. But he was busy, looking at Facebook or something, so I had to, talk to his students. It's the next best thing, I guess. So I assembled a team that knew the science, that knew the math, that knew the physics to solve this problem. Part 1, the setup.
Okay, so in our circuit, we set it up with a battery, a resistor, a capacitor, and a voltmeter, which measures the potential difference across the resistor. When we switched the circuit on, the charge on the capacitor increased, which decreased the current, which also decreased the voltage across the resistor, which we measured using the voltmeter.
Long story short, time's ticking on, and voltage is ticking down. Part 2, the collection. Using state-of-the-art cellular technology, we were able to capture the various data points in order to see a trend. Part 3, the big picture. We plotted our points to see where our data lies, but we noticed a problem. There's a curve. What do?
So we start with our equation of current as a function of time, and multiply it by resistance to make it an equation for voltage as a function of time. This yields a graph that curves. So we linearize the equation by taking the ln of both sides. We simplify by splitting ln of initial current times resistance times e to the negative t over tau into ln of initial current times resistance plus ln of e to the negative t over tau. We simplify ln of e to the negative t over tau into simply negative t over resistance times capacitance. Now, the graph is linear. That means that, if you put the voltage on the y-axis and the time on the x-axis, ln of initial current times resistance is equivalent to the y-intercept, and negative 1 over resistance times capacitance is equivalent to the graph's slope. We can use the values we collected to find the slope, set it equal to negative 1 over RC, and solve for resistance.
Nice. Part 4, the result. So after calculating the slope and plugging in the capacitance, we found out that the resistor is 17,778 ohms. And the actual value is... Part 5, the error.
To calculate our error, we subtracted the actual value, 15,000 ohms, from our calculated value of resistance, 17,778 ohms, and divided that by the actual value. Our value is 18.5% off of the real value, which was outside of the plus or minus 10% error margin.
Long story short, don't ask high schoolers to do shit for you because they're just gonna mess it up, and you could have just used the manual and figured out the number that way and didn't buy a plane ticket to see Mr. Jacobs use Facebook on his computer!